Did you know there are 3 hidden data structures that top coders use? When you type in Google's search bar and see instant suggestions, 3 invisible data structures work together. Tries, predict your words. Union, find, groups related queries, and bit manipulation speeds up the entire system. Most coders know arrays and trees, but top performers rely on these 3 specialized structures to solve specific problems, orders of magnitude faster. Understanding when and why to use tries, union find, and bit manipulation separates casual coders from those who ace interviews and build high-performance systems. In the next few minutes, you'll see exactly how each structure works, where it's used in real systems like Google Search, and when to apply it in your own code. Let's start with trie. It's a tree-like data structure that efficiently stores a dynamic set of strings, often used for rapid retrieval of keys, like in autocomplete features. As you type C in the search bar, the trie immediately traverses its nodes, highlighting the branch corresponding to your input. This allows for incredibly fast, prefix-based searching. Each character typed narrows down the search path, moving deeper into the trie. When we type A and R, the structure quickly identifies all words sharing the CAR prefix. The annotation trie traversal, big O of M, where M equals typed length, means that finding suggestions is proportional only to the length of what you've typed, not the total number of words in the dictionary. This makes it incredibly efficient for large data sets. Next, let's explore union find, a data structure perfect for managing disjoint sets and tracking connected components. Imagine you have several elements, represented by these nodes, and you want to know if 2 elements are connected, or if you want to merge 2 groups of elements. Union find does this by efficiently grouping them, here shown by matching colors. The real power of union find comes when merging groups. When node B connects to node C, the structure instantly unifies all nodes in both the blue and green groups into a single new connected component. The arrows show representative nodes, which help the structure quickly determine if 2 elements belong to the same group. The annotation union find, merge groups, and check membership in big O of 1 means these operations are almost instantaneous, regardless of the total number of elements. Finally, let's look at bit manipulation, a technique for efficiently storing and managing multiple Boolean flags within a single integer. Here we have a 32-bit integer, where each bit can represent a yes or no flag. To set a flag like is premium at bit 0, we use a bitwise OR operation, with a mask created by shifting a 1 to that position, as represented by 1 left shifted by 0. This method allows us to store information like is verified and is active, using minimal memory, as demonstrated by setting bits 1 and 2 with 1 left shifted by 1 and 1 left shifted by 2, respectively. The true benefit of bit manipulation becomes clear when comparing it to using individual Boolean variables. A single 32-bit integer can compactly hold 32 distinct flags. Storing 32 separate Boolean variables would consume significantly more memory and potentially reduce performance. Bit manipulation offers a powerful way to optimize for both space and speed in systems where many simple flags are needed. To ace interviews and build high-performance systems, you need to choose the right tool for the job. These specialized structures are not just academic concepts. They're vital for solving real-world problems efficiently. In the next section, we'll take a deep dive into the trie structure, exploring its construction and how it powers autocomplete features in detail. Let's start with tries. A trie is a prefix tree that organizes words by their letters, making prefix-based searches incredibly fast. Each node in the tree represents a single letter, and branches represent possible next letters. This fundamental structure allows for efficient prefix matching. To find a word, A trie lets you walk down a specific path. For example, to find a word starting with C, we traverse directly to the node representing C. This focused approach avoids scanning irrelevant data. Continuing our path, to build the prefix CA, we then move from C to its child node, A. Each step deepens our prefix, narrowing down the potential words with minimal effort. Finally, completing the prefix CAR, we arrive at the R node. When you reach the end of a word that exists in the trie, a special flag marks that node. This indicates a valid word termination at this point in the path. This structure is why Google's autocomplete can suggest words instantly, even with billions of search terms stored. From the R node, we can quickly explore its subtree to find all words that share the car prefix, such as card, cared, and cargo, efficiently generating suggestions. Now, let's compare the efficiency. Unlike a linear search, which must potentially check every word in a list, a process that takes big O of n time, where n is the number of words, a trie search time is big O of m, where m is the length of the word you're typing. This means the trie only performs steps proportional to the length of your input, not the size of the entire dictionary. It completely ignores unrelated branches, leading to significantly faster searches, especially for large data sets. However, there is a trade-off. Tries use more memory than a simple list, because each node stores pointers to its children representing the potential branches for subsequent letters. This structural overhead contributes to higher memory consumption. But if you're performing many searches, this speed gain is often well worth the increased memory usage. Tries are optimized for frequent, rapid lookups, making them ideal for applications like autocomplete, where speed is paramount. Next, union find. This structure solves a specific problem, quickly determining if two elements are in the same group and efficiently merging groups together. Initially, each element is considered its own group, represented by itself. Instead of storing every connection between elements, union find assigns a representative to each group. When we perform a union operation, we merge two groups by making one group's representative point to the other, establishing a shared connection. Here, we see another union operation, forming a separate group with different elements. Each group maintains its own distinct representative and connection, independent of other groups. Now, when we union two elements that belong to different groups, their representatives connect. This effectively merges all elements in both groups into a single, larger component, all sharing the same ultimate representative. Two elements are connected if they share the same representative. To find an element's representative, we trace its parent pointers until we reach a node that points to itself. This process is called a find operation. Notice that the path length to the representative can vary. For example, finding the representative for C involves a shorter path directly to D. This shows how traversal depth can differ for different elements. This makes connectivity queries incredibly fast, nearly O of 1 time, with a technique called path compression. During a find operation, we can optimize the tree by making all visited nodes point directly to the root, flattening the structure. By compressing the path, subsequent find operations for these elements become much faster, ensuring that the tree remains as flat as possible, achieving nearly O of 1 performance. Without union, find, checking if two elements are connected, requires traversing the entire graph with breadth-first search or depth-first search, which takes O of n time. As you can see, union find provides a significantly faster, nearly constant time solution for connectivity queries, without needing to traverse the entire graph. Union find is used in network systems to detect clusters, in social networks to find friend groups, and in distributed systems to track which servers are in the same cluster. However, the trade-off is that union find only answers, are they connected? It doesn't store the actual path between elements or any associated edge weights. Finally, bit manipulation. This technique uses individual bits in an integer to represent multiple Boolean values simultaneously. A single 32-bit integer can store 32 separate yes or no answers, and operations on bits are incredibly fast. Just single CPU cycles. Instead of storing 32 separate Boolean variables, you pack them all into one integer. Setting a bit means turning it on. Checking a bit means reading its value, and toggling a bit means flipping it. To set bit I in a variable x, we use the bitwise or operation with a mask. The mask is created by left shifting the number 1 by I positions. For example, to set bit 0, we shift 1 by 0, creating a mask where only bit 0 is 1. Then, we perform a bitwise OR operation between our original integer x and this mask. This operation ensures that bit 0 in x is turned on, while all other bits remain unchanged, effectively setting our isPremium flag. To check if a specific bit, like bit 0, is currently on, we use a bitwise AND operation with the same mask. If the result of this AND operation is not 0, it means that our target bit was indeed on. A non-zero result, such as 1, directly confirms that bit 0, representing isPremium, is currently true. This allows us to efficiently query the state of any individual flag. To toggle a bit, meaning to flip its state from on to off or off to on, we use the bitwise XOR operation with the same mask. Here, bit 0, which was previously on, is now flipped to off. And if we toggle it again, bit 0 flips back to on. This demonstrates that XOR reliably flips the state of a bit regardless of its current value, making it highly versatile for managing flags. Bit manipulation truly shines when managing multiple flags. Here, we're setting bits 0, 1, and 2, corresponding to our isPremium, is verified, and is active flags. Notice how 3 separate flags are all efficiently stored within this single integer variable. And just as easily, we can toggle individual flags. Here, we're turning off the isVerified flag by manipulating bit 1, demonstrating precise control over each status indicator. The true advantage becomes clear when we compare this to using separate Boolean variables. Bit manipulation allows us to store 32 flags in just one integer, making it 32 times more compact. Each operation, whether setting, checking, or toggling a bit, takes constant time, or O of 1, and often executes in a single CPU cycle. So, when should you use bit manipulation? Firstly, to store multiple yes-no flags compactly, like feature flags or user permissions in databases. Secondly, for optimizing performance in competitive programming, especially for tasks like subset enumeration. And thirdly, in low-level systems where memory and speed are absolutely critical, such as embedded systems or high-performance databases. However, there's a key trade-off to consider. While bit manipulation offers exceptional speed and memory efficiency, it often results in code that is less readable and harder to understand for developers unfamiliar with bitwise operations. Therefore, use it judiciously, primarily when performance is a critical factor.